Hey everybody, welcome to supplementary video 12.4 to 12.5. Today we're going to be taking a look at cell biology, specifically of the nervous system, in a lot more depth than we go over in the high school portion of this class. So recall from biology, not just the advanced biology high school portion, but from biology, that cell membranes are going to be responsible for controlling what is entering and exiting the cell. Usually, your small hydrophobic particles are able to pass through the cell membrane quite easily, but your large or your charged particles are going to need some help to move with the help of transmembrane proteins. In the nervous system, usually those transmembrane proteins are going to be moving things back and forth to basically create or to remove a charge difference between the inside and outside of the cell, which we'll see the high school in the high school side, video 32, talking about action potentials. A couple of things that we'll add on is that cell membranes can exhibit electrochemical exclusion, meaning that those transmembrane proteins will have a positive charge in the center, which is going to attract a negative charge to move through, or they might have a negative charge in the center of that transmembrane protein, which is going to attract a positive charge and allow that positive charge to pass through. But it's exclusive. So if that protein has a negative charge in the middle, it's only going to allow certain positive charges to come through, and vice versa. Cell membranes, those transmembrane proteins, may exhibit size exclusion, meaning that proteins have a very specifically sized pore running through the center of them that's going to allow only certain size of ions to pass through. Other proteins may be gated proteins, meaning that they do not allow free diffusion. They aren't allowing those particles to move back and forth freely. But once a certain event or a certain threshold is met, then they open up, the gate opens, and then they allow diffusion to take place. So you have several different types of gated proteins. The first is ligand gated channels. They're going to open the gate, if you will, when a signaling molecule, which is also known as a ligand, binds to the protein on the extracellular or outside the cell side. Your mechanically gated channels, they're going to open because of some sort of physical distortion in the membrane. We usually see mechanically gated channels associated with our touch receptors. Voltage gated channels are going to change when there's a change in the electrical charge or in the area around the cell. You also have leakage channels, which are going to open and close quite randomly, and so we call them leakage because they are leaking out ions randomly. So the top left here, you can see how acetylcholine is going to bind on the extracellular side. That's going to open the pore and allow materials to flow through. Here we have a mechanically gated channel, so there's some sort of physical distortion that's going to cause this gate to open. Down here you have your voltage gated channel, which is blocked until a certain threshold is met. So here the voltage is minus 70 millivolts, but once it reaches minus 50 millivolts, that channel opens. And then here we have a leakage channel, which is randomly opening and closing. So still talking about charges here, we needed to talk about graded potentials. So a local change in the charge or the potential of a membrane is called a graded potential. And when I say local, I'm saying in a very, very small area of the cell membrane. The amount of change or the amount of potential that's going to be changing is based on the size of the stimulus. So a stronger stimulus is going to cause a greater change. So you have depolarizing graded potentials that are causing the charge to become less negative. And when you watch video 32, this will hopefully make a little bit more sense when we talk about depolarization and repolarization here. You also have hyperpolarizing graded potentials when the charge is becoming more negative. And so the cell membrane does have a negative charge, but it needs to reach a certain threshold positive charge to be able to fire. If you recall what was taking place during the neuromuscular junction firing, it's very, very similar. And so if you have depolarizing graded potentials, that means you have a certain part of this neuron is receiving a depolarizing charge, which is causing it to become less negative, or you can think it's moving towards the positive. We say that it's becoming less negative because it's starting at negative 70 millivolts and progressing towards zero until it gets above that. Usually depolarization is going to occur because sodium or calcium is entering the cell. Hyperpolarizing causes it to become more negative. Again, it's starting at that negative 70 millivolts. And so if it gets lower, it becomes more negative. Usually that's because potassium's leaving or calcium is entering the cell. And so the graded potentials in all of those dendrites in the neuron, they can be depolarizing or hyperpolarizing, like we talked about. And if they are after the synapse, in the neuromuscular junction, that would be on the muscle side, but you also get neuron to neuron synapses. So this is going to be in whatever the receiving end is. So on the dendrites here. If it's depolarizing, we call it excitatory postsynaptic potentials. But if it's hyperpolarizing, we call it inhibitory postsynaptic potentials. And you can see EPSP or IPSP to abbreviate them here. And so if you sum up all of those EPSPs and those IPSPs together, you're going to determine whether or not that neuron reaches its stimulus threshold. And so they're all going to flow through those dendrites to the soma down to the axon hillock. And at that point, they all kind of come together, and you sum up all of your depolarizing and hyperpolarizing to determine if you reach the threshold and if that message is going to continue on down. So they show here, we're starting at just above that negative 70 millivolts here. In green, we have synapses that are EPSP, so they are depolarizing, which means they're going to move less negative. They're going to move up. You have two that are hyperpolarizing, so they're decreasing, or they're making it more negative here. You sum all of them up, they're all going to travel from left to right here on this neuron. They're all going to come together at that axon hillock right there. And if they do reach that threshold at that minus 55, we will get firing of that neuron. Some neurotransmitter systems we see there's several, excuse me, there are several of them. We're going to talk about the cholinergic systems here. So the cholinergic system is going to be a synapse system based on acetylcholine. We already saw one of them with the neuromuscular junction. Cholinergic systems have two different types of receptors named for the class of drugs that are going to interact with them. So acetylcholine interacts with both receptors, but we've also figured out what other things interact with them. The first being a nicotinic, which is going to be the kind that's found in neuromuscular junctions as well as some other synapses, and it's going to cause depolarization, so becoming less negative. You also have muscarinic. Nicotinic, you probably figured out, is with nicotine. Muscarinic is going to be associated with certain mushrooms. But muscarinic receptors may cause depolarization or hyperpolarization depending on where we're at, what kind of receptor we're dealing with. There's several different categories of muscarinic receptors. Okay. So again, this is just kicking off our nervous system supplementary video. So a lot of it might not make sense until you get through video 30, 31, 32, since it's kind of touching on parts of a neuron that we kind of see in divisions from video 30 all the way to action potentials in video 32. So some of this will start making a little bit more sense. Make sure you're paying attention to the textbook. Again, this is sections 12.4 and 12.5 that we're discussing here. And as always, if you have any questions,